Welcome back, everyone. In the first video of Chapter 2, we finished up discussing subatomic particles after we learned about the atomic theory. And that brings us here in the second video to Part B, where we're going to start talking about cations, anions, and neutral atoms. As we know, atoms have subatomic particles, and some of those subatomic particles, like protons and electrons, have charges. The presence of those subatomic particles in an atom, therefore, can give an atom a charge if they are unbalanced. So if we have the same number of protons as electrons, there is no net charge because we have an equal amount of positive and negative charge. However, if we have more electrons than protons, we would have more negative charges than positive ones, and therefore the entire atom overall would be negative. Now, what if we had more protons than electrons? In that case, we would have a net positive charge because there are more positive charges, protons, than electrons. Now, to simplify matters, we have some terms that help us describe these various situations. The first term is a neutral atom. A neutral atom has no net charge. This happens because we have the same number of electrons as protons. Now, what if we had a charged atom? Well, we refer to charged atoms as ions. Ion is a generic term for an atom that has some kind of a charge. So say, for example, we have a positive atom. We could call that a positive ion. Say, for example, we had a negative atom. We would refer to that as a negative ion. Say we had a charged atom, but we didn't know what its charge was. We would just refer to it as an ion. So there are neutral atoms and there are ions. Now, we also have terms that describe more specifically what type of ion we have. If we have a negative charge on an atom, we could call that a negative ion, or more specifically, an anion. So anions are negatively charged atoms. Now, if we had an atom that was positively charged, we could refer to that as a positive ion, but more specifically, we would say it's a cation. A cation is an atom that has a net positive charge. So let's review. Anions are atoms that have a negative charge. This happens when we have more electrons than protons in the atom. A cation is an atom that has a net positive charge. That happens when we have more protons than electrons. In either case, we can have a multiply charged ion. So for example, we could have a -1 ion, or a -2 ion, or a -3 ion, and so on. That also happens on the positive side. We could have a +1 cation, +2 cation, +3 cation, and so on. How is this possible? Well, remember that electrons have a -1 charge. If we had 1 electron, that would be a -1 charge. But if we had 2, that's a -2 charge. If we had 3, that's a -3 charge. Let's work on a small exercise where we actually determine the charge of various ions. Take a quick look at this table that we're going to fill out. In the first column, I have a list of ions/atoms. This is where we're going to put the symbols and the charges of atoms and their ionic charge. In the second column, I have a place to actually write down the charge. Notice in both of these columns, there are various blank spaces that we're going to fill in. Now, in the last 3 columns, I also have some information about the number of protons, the number of electrons, and of course, the atomic number for the atom. So let's go ahead and do a few of these ourselves, and then I'm going to give you a chance to pause the video and try a few on your own, and then we'll discuss those as well. First, let's do one together. So the first row here, we have the lithium atom. Notice I called this an atom because it's not charged. If it were charged, I would call it a lithium ion. So anyway, we have lithium here, and the charge is 0. And that brings up an important point. Where would we put the charge next to a symbol? If we have a symbol and we want to show a charge, a really good place to do that is up in the top right-hand corner. So you'll notice on the row below, we've got a plus charge right here, indicating there's a +1 charge on that particular ion. Anyway, back to our lithium example. We have a neutral lithium atom, and lithium has an atomic number of 3. That means that lithium has 3 protons. Now, if the charge on this lithium atom is 0, and there are 3 protons, how many electrons are there? That's right, there must be the same number of electrons as there are protons for the charge to be 0. So if there are 3 protons, that means there are 3 electrons as well. Let's go to the next row. Here we have a lithium plus 1 cation. Notice I called it a cation because it has a positive charge. What is the positive charge? It's plus 1. There's a single positive charge on this lithium cation. Now, has the atomic number of lithium changed? No, for lithium to be lithium, it has to have an atomic number of 3. That means there are 3 protons on lithium, always. So if the number of protons hasn't changed, but the charge has, what has changed? That's right, the number of electrons. If we have a cation, do we have more protons or do we have more electrons? That's correct, we have more protons. How many more? Well, it depends on the charge. Here we have a plus 1 charge. That means we have 1 more proton than electrons. So how many electrons do we have? That's right, 2. Now's a good time to pause the video and see if you can do the third row yourself. When you unpause the video, we'll discuss this one together. Here in the 4th row, we're given the charge and the atomic number. From the atomic number, we can determine the identity of the element. How do we do that? We look at the periodic table and we try to find element 17. Notice it's chlorine. Chlorine's atomic number is 17, which means it has 17 protons. Now we just need to figure out the rest of the empty cells. Because we have a -1 charge, we're dealing with an anion here. And anions have more electrons than protons. We see the negative charge is 1 negative. That means we have 1 more electrons than protons. So if we have 17 protons, that means we have 18 electrons. If you got that one right, great job. Now, you should pause the video again and try the next row. In the next row, we're only given the number of protons and the charge. From this, we have to figure out the atomic number, the number of electrons, and the identity of the ion or atom. Let's start with the number of protons. We see there are 7. This means we're dealing with something that has an atomic number of 7. What element has an atomic number of 7? That's right, we can look at the periodic table to find out. Here we see that nitrogen is the element with atomic number 7. It has 7 protons in its nucleus. Now we see that this particular species has a -3 charge. That means we're dealing with an anion. Now we just need to figure out how many electrons this nitrogen with a -3 charge has. Because it's a -3 anion, that means it has 3 more electrons than protons. So if we have 7 protons, that means we have 10 electrons. If you got that one right, great job. Let's go to the next row. Here, we're not given the atomic number or the number of protons. However, we do know the charge and the number of electrons, and from this information, we can figure out which element we're dealing with. Because the charge is -2, we're dealing with an anion. That means we have 2 more electrons than protons. So if we have 18 electrons, that means we have 18 minus 2 protons, or 16. So our atomic number is 16 because we have 16 protons, and that means we're dealing with sulfur. And because this sulfur has a -2 charge, it's an anion, and we'll write the charge up here. Let's try the last row. Here we're also given the number of electrons and the charge. However, the charge here is positive. That means we're dealing with a cation. Now we see that there's a +2 charge. That means there are 2 more protons than there are electrons. So if we have 78 electrons, that means we must have 80 protons. And that's how we know we're dealing with a mercury +2 cation. In addition to charge, some subatomic particles also contribute mass to an atom. We call the mass of an atom its mass number. And it's this mass number that we're going to discuss next. Atoms have a quantifiable mass that is determined by adding up the masses of the particles that it is made from. We call this the mass number. Specifically, the mass number is the sum of the protons and the neutrons in the atom. So why protons and neutrons and not electrons? Well, electrons, unlike protons and neutrons, have an insignificant mass. We learned that the mass of an electron is about 1 over 1,000 times the mass of a proton. So when we want to find the mass for an atom, we only want to consider the massive particles from which they are made. And the massive particles are the protons and the neutrons. Let's go to the next page and look at some examples of how the mass number is determined for an individual element. There's one more term about atoms that I need to teach you first before we look at some specific examples using mass number, and that term is the word isotope. We use the word isotope to describe atoms that are of the same identity but a different mass. It turns out that you can have identical types of atoms, but they can weigh different amounts. How does this happen? It happens when we have two different atoms with the same number of protons. That's what makes them the same type of atom, but they have a different number of neutrons. For example, suppose we had 3 different carbon atoms. Each of these carbon atoms would have 6 protons in it. To help us keep track of that, I'm going to write the 6, which is the atomic number for each of these carbon atoms, in the bottom left-hand corner. This 6 represents the number of protons in each of these atoms. Now, it turns out these carbon atoms don't necessarily have to have the same mass. To help us keep track of the masses for each of these atoms, I'm going to write the mass number here in the top left-hand position. This style of writing the element symbol with the mass number in the top left position and the atomic number in the bottom left-hand position is called isotopic notation, and it's used when we want to compare isotopes specifically. So here we have 3 different carbon isotopes. We have the carbon-12 isotope, the carbon-13 isotope, and the carbon-14 isotope. Notice they all have 6 protons. Can we figure out how many neutrons are in each of these? Yes, we can subtract the number of protons from the mass number to determine the other massive particle, that is, the number of neutrons. So for the carbon-12 isotope, we expect there are 6 neutrons because 12 minus 6 is 6. For the carbon-13 isotope, we expect there are 7 neutrons because 13 minus 6 is 7. For the carbon-14 isotope, we expect there are 8 neutrons. Let's go ahead and practice that skill with some examples in the table below. Go ahead and pause the video and see if you can take a look at this isotopic notation for carbon-13 and fill in all of the blank cells for that particular isotope. When you unpause the video, we'll discuss. Because there's no charge indicated on the symbols, we know that the charge is 0. We have a neutral isotope. The number of protons is given to us from the atomic number, so it's 6. And we know since the charge is 0 that we have the same number of electrons as protons, so also 6. And the number of neutrons, we can find that by subtracting 6 from 13 to give 7. This gives us our mass number of 13. So if you got that right, great job. Let's go and try the next column. Here we have the number of electrons, the number of neutrons, and the mass number. What should we do first? Let's start with an empty box to place the symbol that we ultimately figure out for this problem. We know the mass number, so let's put the 31 in the top left-hand position. What else can we figure out right now? From this, is it possible for us to figure out how many protons there are? Well, we definitely can. Since we know the mass number, which is 31, and we know the number of neutrons, which is 16, we can figure out the number of protons. If we take 31 minus 16, we get the number of protons to be 15. Now we can figure out which element this is. Looking at the periodic table, we see that the element with atomic number 15 is phosphorus. Now there's one more missing space here, that is for charge. How do we figure out the charge of this particular species? Well, we look at the number of electrons and the number of protons and we compare. Notice there are 3 more electrons than protons, giving us a charge of -3. Now let's try the last column. Here we can start by figuring out the number of protons. Since we know the charge, we know that there is 1 more electron than there are protons. We know there are 36 electrons, so there must be 35 protons. If our atomic number is 35, that means we're dealing with the element bromine. How do we figure out the mass number? We add together the number of protons and the number of neutrons. That gives us 77. So now we know quite a bit about the structure of atoms. We also understand their mass number as well as the concept of isotopes. Understanding this information is going to help us a lot when we look at the periodic table and try to find certain information. To show you what I mean, let's go to the next page where we'll discuss average atomic masses and how that relates to isotopes. When you look at the periodic table, you'll find there is a lot of information. For example, we see symbols, we see column numbers, we also see the atomic number, and then we see this number right here. What is this number? Well, it turns out this is what's called the average atomic mass for a given element. For example, a hydrogen atom, which has 1 proton, for some reason shows an average atomic mass of 1.008. Helium, which has 2 protons and 2 neutrons, shows an average atomic mass of 4.003. Now that's an interesting problem. Why are we seeing masses that are not whole numbers if subatomic particles like protons and neutrons are indivisible? Well, to answer that question, I have to explain to you what the average atomic mass is and how it's derived. It turns out that the masses listed for elements on the periodic table are averages. They're averages that are calculated from the known abundances of naturally occurring isotopes. So for example, we looked at carbon before, and we saw there were 3 isotopes of carbon. Some of those isotopes are heavier and some are lighter. It turns out natural carbon comes in all 3 varieties, some more common than others. That's called the natural abundance of an isotope. So when we look at the periodic table, we're looking at the results of a calculation that takes into account all of these different isotopes for a particular element, their natural abundances, and then puts together an average mass that we can use in our calculations when we're studying various phenomena. Let me show you how this works. First, it's important to realize that the average, when we calculate it, is not a simple average. If it was a simple average, we would simply add up the individual atomic masses for each of the elements that go into the calculation, and then divide by the number of species we're adding together. So for example, if we have 3 isotopes of carbon, a simple average would just take up the masses of each of the isotopes, add them together, and then divide by 3. This would not give us the type of average that we're looking for. What we're looking for is something called a weighted average. A weighted average is much like the average that we give you to calculate your grade. Some things are weighted heavier than others. For example, you might take a class where exams are much heavier weight than quizzes, and therefore most of your grade comes from the exams and a little bit from the quizzes. It's the same thing with average atomic masses. We want to give more weight to the more common isotopes. So let's see how this works using neon as an example. Neon has 3 isotopes, neon 20, neon 21, and neon 22. First, we need to find out what the relative abundances are of these individual isotopes. Someone would have to do an experiment to measure that, and you would have to be provided with that data, of course, to know what it is. For example, neon 20's natural abundance is 90.48%, compared with the other 2 isotopes, which are 0.27% and 9.25%. To start, let's write out the symbols and the number of protons, the number of neutrons, and the mass of each of these isotopes. After that, we'll figure out what the weighted average would be. For the symbol, we're just going to write the symbol neon in the isotopic notation, so we have neon 20, neon 21, and neon 22. Those are the mass numbers for each of these isotopes that were given in the name. Remember, mass number always goes in the top left-hand position. How many protons does a neon atom have? That's right, the atomic number for neon is 10, so each of these isotopes has 10 protons. From the mass number and the number of protons, we can determine how many neutrons there are in each of these isotopes. Neon 20 has 10 neutrons, neon 21 has 11, and neon 22 has 12. Let's write down the mass for each of these isotopes. It's 20, 21, and 22. So when we're calculating the weighted average, most of the mass, 90% of it, will come from the neon 20 isotope. 10%, around that, will come from the neon 22 isotope, and a very small part of that will come from the neon 21 isotope. Let me show you the exact process for how we go about calculating this weighted average. To find the weighted average, we're going to add the individual contributions that each isotope makes to the weighted average. For example, the neon 20 isotope makes up 90.48% of the total abundance, and it has a mass of 20 AMU. So if we take 90.48, divide it by 100 because it's a percentage, and then multiply that by the mass, which is 20 AMU, that would be the contribution to the overall average mass from that particular isotope. Now we just have to come up with the other isotopes and their contributions. Pause the video and see if you can actually figure out the remaining terms in this calculation. When you unpause the video, of course, we'll discuss. So here in the second term, we have to add in the contribution from the neon 21 isotope. The neon 21 isotope has a relative abundance of 0.27%. So if we divide 0.27 by 100, that's its abundance, which we're going to multiply by the mass of this particular isotope. The mass of this isotope is 21 AMU. So that's our second term. In the third term, we're going to add in the contribution of the neon 22 isotope. The neon 22 isotope has a relative abundance of 9.25%. So if we divide 9.25 by 100 and then multiply that by the mass of 22 AMU, we get the contribution of that particular isotope. We can now determine the average mass for the element neon, taking into account these three isotopes. When we add each of these terms together, we get a calculated value of 20.1877 AMU. Now we just have to figure out how many significant figures this calculated value should be rounded to. In some of our terms, we have measurements that will necessarily involve significant figures. For example, the percent abundance in each case has some number of sig figs that we need to take into account because it's a measurement. The mass number for each of the terms, however, is exact because it's a counting number. Taking this into account, our first term should have 4 significant figures, the second term should have 2 significant figures, and the third term should have 3 significant figures. Notice, however, that we're adding these 3 terms together. That means we need to follow the rules of addition. To follow the rules of addition, we need to find the place value that each of these terms goes out to, and that will be our limiting digit. Notice the first term goes out to the 100th place, so does the second, and so does the third. That means our calculated value is limited to the 100th place as well. When we round this value up, we get 20.19 AMU. How does that value compare with what we see on the periodic table? Well, it turns out that will depend a little bit. It depends on which periodic table you're looking at and where they originated their values from. In our case, we might have been rounding values that had some estimations that some other periodic tables might have more precise values for. So it depends, and that's why we want to stick to one periodic table for our class while we're doing calculations. This is to eliminate any potential error from this kind of thing. So with that, I'm going to wrap up this lesson. I hope you enjoyed it, and please let me know if you have any questions. I will see you in the next video.